Hi, welcome to the Calculus 2 lecture series. And we are in the unit number 4, sequence and series. This is a big unit. We are in the lecture number 19. They'll talk about the alternating series. And this is the video number 3 for this lecture. So in this video, we're going to talk about the two kinds of the divergent. One is the absolutely convergent, and the second one is we call this a conditional convergent. Okay, so let's take a look. Let's go ahead and start our lecture notes, and let's take a look at what is the differences between this, these two type of the convergences here. All right, so now let's take a look. What is the absolute convergence here? So when the absolute convergence here, so here we say when a series here, so for this series summation n from 1 to infinity is called absolutely convergent if the series of the absolute value and let me see, if I take the absolute value of the an for the n from 1 to infinity, if this series is convergent. Okay, so then we call this is absolute convergent. That means if you take the absolute value of the series. So that's why we put these topics under the alternating series, because the alternating series we know it has negative, positives, right? So what happens if you let it all become positive, put absolute values here. So if this is what we call this absolutely convergence, if the absolute value convergent. And what is the conditional convergence here? So we say a series summation an, and to the an is called conditional convergent. Okay, if it is convergent, absolutely. If it is a convergent but not absolutely convergent. Okay, so that means the summation n from 1 to infinity, this one converges, right? So this one will converge, but if you take the absolute value of the an, is not as diverges here. That's why we call it is the conditional converge. That means this one will converge, but if you take the absolute value, it's not going to converge, it's diverge. So we call this a conditional. Okay, so now let's take a look at some example, and then we kind of get familiar with this definition about the absolute convergent and the conditional convergent. So, the problem number 1 is that is the alternating series n from 1 to infinity, -1. Remember when you see the -1 to the n-1 power, this is we call this alternating series. So let's say, is this series convergent absolutely? All right, so that means we know the convergent absolutely. That means if you take the absolute value. So let's see here. So this is n from 1 to infinity. I'm taking the absolute value of my series. So this is n-1, and this is n squares here. So I know if you take the absolute values here, right? So the -1 to the n-1, what are going to be is positive, right? So this will be equal to the 1 over n squared. Then when you see this, then I say, oh yeah, this is a convergent series. Why? Why? Because it is a what? It is a P-series, right? So it is a P-series with a P equal to 2, which one is greater than 1. So by P-series theory, we know it's a convergence. Right? So because this is convergence, so I know, so that's why the n from 1 to infinity, the n square, -1 and -1, this is absolutely convergence here, right? Because if you take the absolute value is a convergence here. So in here, because this one's here is what? This is a P series, right? So because it's with P is greater than 1, then we know this is a convergent series. Because this is a convergent, that's why we know this series is absolute convergence here. All right, let's take a look at the second one here. So the second one's it will tell us that is the alternating series is absolute convergent or conditional convergence here. Okay, so now let's take a look here. So from this is alternating, right? So and also it's decreasing. So let's say here, so then I said the limit n approach to infinity, the 1 over n. So what is this one here? Will approach to 0. Right? So the 1 over n approach to 0, so I know n from 1 to infinity, and this is -1 to the n minus 1. We know this is a convergent. Why? Because by the alternating series test, right? So we know the alternating series test, that means if you let the an term, the limit an approach to infinity, if it's approach to what? If this one is approach to 0, then I know this is a convergence because of alternating series converging. So I know this alternating series is converging. Okay, now let's take a look. If I put the the absolute value in here, what happens? So you said n from 1 to infinity. Now I put the absolute values here. Let's see here. This is -1 to the n minus 1. This is n. So what is this ones here? This will be giving you n to the 1 to infinity, 1 over n, right? Because the 1 over -1 to the n minus 1 exponents, that will be, so you take the absolute value, it's always be 1 positive. So what is this series? This is what? This is a divergent series, right? So this is a divergent series. Why? Because it is what? It is a harmonic. All right. So we say it is a harmonic series, and harmonic series is a what? Is a divergence here. Okay, so like in here we see, so you see, we see one is a divergence, right? Because this one, when you take the absolute value, is a divergent. So I know this is not absolutely convergent. So what is the conclusion for this one? This is a conditional convergence, because it is a converge at this series, the alternating series. But if you put the absolute value, it diverges here. So this is what we call is the conditional convergence here. All right. So now here we called is convergence series here. So what's that mean? So this one's, it means here, we said if I have a series here, n from 1 to infinity, an, right? Yes, absolutely. Convergent. Then we know it is convergent. Right, so this series, in fact, is pretty easy to prove, right? Because we said an is always going to be less than or equal to the absolute value of an. So if the absolute value of an is convergent, then that's why the an is a convergence here, right? Because when you talk about if the, if this is absolute convergence, that means summation an, the absolute value from n to infinity, this is a convergence, right? So that's why we said if it's absolute convergent, it is convergent. It's kind of pretty, like the kind of easy to prove and the intuitively makes sense. All right, let's take a look at this one. So we want to decide is this series is a convergent or divergence here. So as you can see this series, right? So if I put this is a summation n from 1 to infinity, this is a cosine n and the n squares, right? And so this one you put it like you would say the cosine 1 plus 2 to the square, cosine 2 plus cosine 3, and the 3 to the square, okay? So we know this series has both positive and negative because of cosine value, but it is not successive. That means that's not alternating. So sometimes, they will get a two positive, one negative, or one negative, two positives, right? So even they have a positive and a negative, but it's not alternating, right? So I cannot use the alternating series to test it's a convergent or divergence. Did you see here? So this one here is not alternating. It's not an alternating series. Even some of the values positive, some of the values negative. So I cannot use the alternative series test to test it. So now let me see here. So what happens here, right? So if I say, let's put the absolute value cosine n squares here. Let's see what happens here. So let's see here, the cosine n squared. So I know if you put the absolute value, cosine n is always less than or equal to what? 1 over n squares, right? Because the cosine value is between -1 and the positive ones here, all right? So then I know these ones here, I can rewrite this. This is n to the infinity, 1 over n squared. And then I know for this series, right? So I know this series is a convergence. Why? It's because this is the P series, right? So P series is convergence with P equal to 2 greater than 1. So because of this series is a convergence, that means this series is a what? This is a convergence series. Right? Because this is a convergent series, this is the absolute value of my original series. So I know the n from 1 to infinity, the cosine n squared. What is here? This is a convergent, absolutely. Right? So because when you put the absolute value, this is a convergent absolutely. Because this is a convergent absolutely by the convergent series, so I know this series here is a what? Is a convergent or divergent? Is a convergence here. All right? So be very careful, right? So for this example, I know the cosine n over n squared, even they have a positive and negative, but it's not alternating. So I cannot use the alternating series test to see it's convergent or divergent. So what I'm doing here, I'm trying to see. So that's why I put an absolute value here, right? To see it's convergent absolutely or not. If it's convergent absolutely, then by the convergence theory, I can say it is a convergence here. Okay, all right, that's good. So now let's take a look. The problem number 4, we have the three different series. Let's take a look. Is each one they are convergent, absolutely or conditionally, or is divergent, right? So let's take a look at part A here. So let's first things here. Let's see here. Let's put it into the absolute value, because I know if it's absolute convergent, then it is what is a convergence here. So this one's here, right? So this one will be equal to what? N from 1 to infinity, 1 over n cubed, because this is a negative sign, right? Because this negative sign, when you put it into the absolute value, it's just be positive. And then we see this one's here. So what is this one? This pink, so what is this one? This is a convergent series. Why? Because since it is what? It is a P series with P equal to 3 is greater than 1, so convergent. Right, so this is the P series. So because this is a convergent 1 over, so this green one, so we know this is a convergence, right? So because the absolute convergence, then I know from here, n from 1 to infinity, negative 1 to the n cubed. This one we can say is what is absolutely convergent here. All right, so it's a pretty, so pretty easy to do. And then the next one's here. Let's see, this is a summation n from 1 to infinity. Okay, so here first still we do the same. Let's put the absolute values here, right? So this is negative 1 to the n, and this is n to the what? Cube roots here. So after that, this is n from 1 to infinity, negative 1 to the n power become positive. This is n to the cube roots. Yeah. Okay, now let's take a look. So this series, right? So this is 1 over n cubed. So what type of the series is this one's here? This is a divergent. This is a divergent series. Why? Because it is what? It is what type of the series? It is a P series. And what is the P here? The P here is 1/3, right? Because n to the cube root is P is equal to the 1/3, which is less than 1. So by the P series, we know less than 1, so is what? So it's a divergent. So I know this series is a divergent. If this series is a divergent, then we know this series is what? Is a divergent. Okay, if this series is a divergence, now I know n from 1 to infinity, this is negative 1 to the n and the n to the cube. What is this one, sir? Because this absolute is the divergence, right? So I know this one is not absolutely convergent. right? So be very careful. So I know this one is not absolute convergent. Okay, if it's not absolute convergent, then we will just take a look whether it is convergent conditionally. All right, so for this ones here, so if I let the limit n approach to infinity, so 1 over n to the cube roots here. So what is this one going to be? This one is going to be approach to 0. Because this is approach to 0, so I know n from 1 to infinity, and this is negative 1 to the n to the cube, right? So now I know what happens. So what happens here? So I know this series is what? This is a convergence series. Why this is a convergence series? By what? By alternating series test, right? Because the alternating series test is you test the n part to see that since approach to 0 now, because this is approach to 0. So I know this is a convergent series. All right, so now in here we said this one is not absolute convergent, but it's a convergent. So what is our conclusions here? So we will say that by combining both these two results, so I know this one's summation n from 1 to infinity, negative 1 to the n to the cube. So what do we say this? This one we say is a conditional convergent. Okay, because it's not an absolute convergent, but it's a convergent by itself without the absolute value. So I know I can make a conclusion. I say this series is what? Is a conditional convergence here. Okay, all right. So now let's take a look at the part C here. Part C, okay. So part C, let's take a look here. Like we said always, okay, let's see, you see these alternating things. And now you put like into the absolute values here. This is n, 2n plus 1. And this is negative 1 to the n, right? So this ones here will be n equal to 1 to infinity. Then this is n, the 2n plus 1. Okay. All right. So here, because the negative is to the nth power, you put an absolute value, it's just become positive, right? Then let's see here. All right. So for this ones here, I know this series, this is a divergent series. Why? Why? We'll say by divergent test. So by the divergent test, because the limit n approach to infinity and 2n plus 1 is equal to what? Equal to 1/2. It's not equal to 0. Remember the divergent test say if the an not equal to 0, right? When n approach to infinity, an not approach to 0. So we know by the divergence theory, this is a divergence here. Okay, so because this is a divergence, right? So because this is a divergence, so we can conclude in here, so this is summation n from 1 to infinity, negative 1, the n, 2n plus 1 is not absolute. It's not absolutely convergent. Okay, so now let's take a look because it's not absolute convergence here, right? As a highlight here is not absolute convergence. Okay, so now let's take a look just by itself. Now what happens here? So let's just take a look without absolute values, right? So here, this is -1 to the n, the 2n plus 1, just by looking at the alternating series. So let's take a look again, limit n approach to infinity, and the 2n plus 1. I'll be darned, this one is still equal to 1/2. It's not equal to 0. So what we can conclude for here, so we know this one here is a divergent or convergent. This is a divergent series. Again, right? So this is a divergent series again, and it's because of what? It's because by what? By the divergent test. Okay, so this is a divergence here. So we know this is a divergent, this is not absolutely convergent. So what is my final decision for this series? N from 1 to infinity. This is -1. This is the to the nth power. Right? So this is a -1 n 2n plus 1. So what type of the series here? This is a divergence here. All right. Okay. So this is what we talk about in this video. Is we talk about is what is the absolutely convergent and what is the conditional convergence, right? So absolute convergence here, that means if you put the absolute value for every term of your series, if it's still convergent, and then the absolute convergence will guarantee it is a convergence here, right? The series itself will be convergence here. All right, that's it. That is about the alternating series. And in fact, I like the alternating series very much because it's kind of easy to determine the series is convergent, divergent, and the absolute convergent is very helpful. Sometimes, if you have a positive and negative numbers, even it's not alternating, then you'll be able to use the absolute convergence to guarantee the series is a convergence here, right? All right, that's it. And so the next lecture, we're going to talk about a comparison, the ratio test. That's one of the tests. It's really very handy also. All right, have a good day and nice talk to you, and looking forward to talk to you in our next lectures, series here. Okay, bye. Have a good day. Bye-bye.